I want to start today with a little bit of terminology, something that I think is helpful, but only helpful maybe 3 years from now. And I bring this up to you guys because I know that it shows up in college, and the professors will expect that you know what they're doing, even if, you don't. I referred to this yesterday as, a fraction, and then we used other words to describe it. I want to make sure that you you have some focus about the vocabulary here, because some of you are in calculus and have completed calculus, but vocabulary is important, and I think it appropriate that we have some vocabulary. dx dt is the differential expression of velocity. I'm using that word very specifically. This is a differential, and it's a differential representation of velocity. The same way dv dt is a differential representation of acceleration. The reason I'm saying this to you is there's going to be a time in your future where you'll be faced with something that looks like this. The left side is a constant times acceleration, and the right side is velocity times time. And you'll be asked to create a differential equation. All they're asking for is for you to find a differential that you could substitute into that equation to make it an expression that contains a differential. That's all a differential equation is. And all they are expecting you to do is write the differential term that matches one of the other variables in the expression. So the a changes to dv dt because that's the differential representation of acceleration. Creating a differential equation, not that hard. Knowing that that means to substitute a differential in, worth 1 to 2 points on the AP exam. It's not particularly hard, and there's more work to do from here. But it's not particularly hard to get started. Now, part of the reason I'm being careful is there's a lot of terminology and expressions, and it's going to start getting complicated. Not so much in my class, but keeping straight my class from calculus, because we do things a little different. For example, if you're looking closely at this, you might recognize that there is, a chain going on here, right? The acceleration is the derivative of velocity with respect to time, but velocity is the derivative of position with respect to time. So it is possible that I could write the acceleration as the operation of the derivative on the differential of velocity. Remember when we wrote this out, that's applying the derivative. Take the derivative of this expression with respect to t. Well, the function of v is dx dt, so I've just substituted in the function, which was a differential. Well, calculus has kind of some sillies in it. They'll write that like this, which really makes absolutely no sense. It's not like the d's are actual variables and they can be squared. What this really is saying isn't d squared x over dt squared. What it's really saying is take the second derivative of position with respect to time, meaning take one derivative and then take another. So this symbology is a way of writing an order to a differential. The first derivative is considered a first order differential. The second derivative is considered a second order differential. Now, some of this you know. This is a second order polynomial because the t is squared, right? The order is based on the highest exponent in the polynomial. Differential equations, they can be the same. I can have this is a second order differential equation. The order refers to the highest number of derivatives applied to the function. Now, this becomes very cumbersome when writing it out. You're seeing that, right? I mean, all of this just to say second derivative. So there are shortcuts. There are ways that these are often written. One of them is called dot notation. First derivative is the function with the dot over top. Second derivative is the function with two dots over the top. Dot notation is famously used in engineering and first-year physics classes. We won't use it here, but it is quite possible your professors might, and expect that you know it. Dot notation refers to a derivative with respect to time only, and the dot over the top refers to the number of derivatives. I'm showing this to you because it comes up, and I don't want you to be blindsided by it, but your professor might think you already know this. Some schools teach this. Not any in Hillsborough County that I know of, but I know some in other counties that do. Now be careful, somebody in a third period brought up a very good point. And those of you in calculus or have already had calculus might know what I'm about to do next. This is symbology that's used in calculus. This is saying that I have a function where x is the functional variable. An example of that would be fx equals ax squared plus bx. This would be a function where x is the functional variable. All the functions I've had up here could be argued to be functions with t as the functional variable. But calculus tends to like x. Prime notation says that this is the first derivative of my x function with respect to x. So if they put a little prime there, they mean that that's the first derivative. We won't use any of that in class, but you're going to see it in calculus. So you could have f double prime with respect to x. That is the second derivative. And then give it a couple of weeks and you'll have g of x and f of x. It's fun stuff. Not really. Or f of g of x. Right, all of you have finished calculus AB. You've seen all this stuff. It's a lot of fun. All of these things, different ways of expressing the same thing. So I don't want to belabor this too much. I've gone on about it for about 9 minutes now, but I want you to understand that there's lots of different ways that these symbols can be used, and they're all trying to express the same thing. In this class, we will stick with some basics. Our differentials will always be written as fractions. And although it is possible that we will write and use second order differentials, won't be till next semester. I do want you to know, though, that these commit to memory. dx dt is velocity, and dv dt is acceleration. Commit them to memory. Today we're going to practice. Yesterday we did a motion equation, right? Right at the end of class, we took the derivative of one of the motion equations, and surprise, surprise, we got the other motion equation. If you were paying attention yesterday, I hate the idea that I'm going to do this again in front of the class. But I want to make sure that we're all in the same place. So for those of you who slept through yesterday, let's start right at the end of class. That one's on the board, right? And I said I would like you to take the derivative of both sides. So that would have meant taking the derivative of the function of x with respect to t, which means taking the derivative of all of this. I gave you a method to do this. The polynomial process for doing a derivative of a polynomial. And to do it, I said to you guys that you're going to take and distribute the derivative and just apply this process. The process itself is not hard, but I want you to apply the process. And the process was straightforward. I said, with respect to x of ax to the n would be a times n x to the n minus 1. That's the process for taking a polynomial derivative. Not hard. So if we apply that here, and I've been writing it out the whole time because I'm trying desperately in the very beginning to make sure everybody has access to this. So I'm distributing. I'm taking the constants out away from it and applying the derivative just to the part of the function that matters, the part that has t. The constants come out front. Now, x naught doesn't have a variable with t in it, so we create one. It's a polynomial, so we can have 0 as an exponent in a polynomial. Every term can have t in it, even if it's t to the 0 power. Now, we know that this is going to be the velocity because we've taken the derivative of position with respect to t. Yes?
Why is there an equal sign on the...
It should be a plus sign. Talking and writing at the same time, apparently not my forte today. Now, you're just applying the polynomial method. So with each one of these, first thing I'm going to do is bring the exponent down, subtract 1 from the exponent. Next one, the same thing. And I know we did this yesterday. The exponent's not explicitly there, but if it isn't 1, then a 1 is implied. Bring the 1 down. And the last one, I'm going the extra mile here, but once I bring the 0 down, it wipes out the whole term. That shouldn't be a surprise. We were taking the derivative with respect to time of a constant. We were asking the math to tell us how the constant changes with respect to time. But constants don't change with respect to time. That's why it's got to be 0. But we've done the calculus portion now. Now you just have some algebra to clean up. And when you clean up the algebra, not a surprise, right? Now, you could go one extra mile here. You could take the derivative with respect to time of the velocity. This should give you the function that is the acceleration. Again, it's right at the end of class yesterday. Not tough, I hope. Take my derivative and distribute it to each term. Should be no surprise here. I'll find that dv dt equals a. It has to. That was the definition. That's where we started. Are we all good here? Yeah.
Sorry, can you just scroll up like a little bit? Thank you.
Am I going too fast?
No, I just did get like the last
Okay.
part of the derivative.
No worries.
Thank you.
Now, that brings us right up to where we ended yesterday, correct? It's a little bit of refresher, making sure I'm being deliberate and patient with everybody. So I want to bring some things together here. A was a constant. So V was AT plus V naught. X was 1/2 AT squared plus V naught T plus X naught. Calculus is the algebra of functions. We took the derivative of the position function and got the velocity. The slope of the velocity graph was the acceleration, so when we took the derivative of velocity, we got acceleration. I'm saying this very clearly because we started with one function, and using a process, we got a new function that describes all the slopes of the other function. The algebra of functions. How are functions related to each other? That's what calculus is about, and that's what it generates. Today, I'm going to have you guys do some practice. I'm going to see if you guys can apply what we've just discussed, but we're going to do it in a more complicated way. So here's what I want you to think about. Here's a function of position. Hold on. That's what I wanted. Yeah, that's what I want. This is our position function. I want you to imagine a problem that sounds like this. What is the speed of an object when its acceleration is 0? Everybody hear the question? I want to know the speed of an object when its acceleration is 0. You have an expression for position. You should be able to generate an expression for velocity and an expression for acceleration, starting with an expression for position. Once you have that, answering my question shouldn't be too hard. So, in order to answer this question, we're going to have to figure out an expression for velocity, which means we'll have to take the derivative of the position function. Now, this first time, I'm going to be super explicit, but I'm going to stop being explicit pretty quick. First thing I want to do is what we've been talking about. I'm going to distribute my derivative to each of the terms. And of course, if you know what you're doing here, you should be bypassing me completely and get it done. There's no reason to wait for me to do this. I apply the derivative to each of the terms. Now I have to apply the rules for how to take the derivative of a polynomial. So bring down the exponent, and then generate a new exponent by subtracting 1. Continue to the next term, bring down the exponent and subtract 1 from the exponent. Continue to the next term, bring down the exponent, subtract 1 from the exponent. Continue to the next term, which zeroes out the term because we bring down to 0. Clean up and do your algebra. And we generate a new function. Okay so far? No problems? So you should be able to go one more step, right? Do you need me to do this one too? Or can you take the derivative with respect to time of v? How do you need me to do this one too? Be honest, because I'm kind of done already. I'll do one more. But then I'm going to expect you guys to not need all of this. Just so you know, I would not, in the future, expect this much work to be done to do these. Most of you who have done this before realize that there'd be no reason to do all of this. Completed it all. Do my algebra. We all here? Are we good? All right, so we started with one function and we generated two more. The question didn't ask that. The question asked how fast is the object going when the acceleration is 0? But you can't do that question until you have an expression for the velocity and an expression for the acceleration, which I now have. I can find out when the acceleration is 0. Can you? You should be able to do so. I put 0 in for the acceleration. Find out when that is. Now, if I want to know how fast it's going, well, got an expression for velocity. I'll plug it back in there, figure out how fast it's going. Is that okay? Kind of see where we're going with this? Yes, ma'am. Just like this, you'd be given a function, and then you might be asked to find the expressions for the other functions. That's what we just did. And then you might be given a situation like we just had. It could be like, where is the object when the acceleration is 0? Or how fast is the object going when it's at the origin? These are all different ways of relating the three expressions together. Now, just to be aware of a couple things. This problem where I said, find the velocity when the acceleration is 0, we're only going to look at functions that have acceleration, velocity, and time, like these. But there are meanings to other derivatives. The derivative of the acceleration is called the jerk. It's an actual measurement. It's the third derivative of position with respect to time. If you work on car engines, the rate at which the car engine begins to accelerate has value because it puts stress on the motor, and the amount of stress on that motor can cause it to fracture and crack under pressure. So we look at other values like that. We in this class are going to focus just on these three. They're the only ones that are a part of our curriculum. But other formulations and other physics classes or deeper physics classes will go into more of this. Also, I hope you recognize a couple things. And if you don't, let me help you out. That's initial position. Right? That would be the position at time equals 0. This is initial velocity. That would be the velocity at time equals 0. And in this case, this is the initial acceleration. It would be the acceleration at time equals 0. This problem, the acceleration is changing. It's not a constant, which is why these motion equations that we used to have up here, they're gone. Because if the acceleration is changing, you can't use any of those. But you'll notice something important here. We lose the initial position when we take the derivative of the position function. Meaning you don't know where it started. And you lose the initial velocity when you take the derivative of the velocity function. We already said this earlier when you were looking at velocity graphs. The velocity graph can't tell you the initial position. That information was stripped away. That 4 is gone. Similarly, we can't look at the initial velocity if all we have is an acceleration function. We often call these things boundary conditions. I will also call them initial conditions. Because if you haven't put it together yet, what I'm really going to ask of you is I'm going to ask you to go not just in this direction, but I'm going to ask you to go in this direction as well. Can you do the process backwards? You're going to have to. The going backwards is finding the antiderivative. So if going forwards meant pull down the exponent and subtract 1 from it, going backwards is going to mean to add 1 to the exponent and divide by that new exponent. So when we're going from position to velocity, we take the derivative. But if you're going velocity to position, you take the antiderivative. Now, I think you guys probably need a quick practice real quick just to make sure that this is hitting home correctly. So let's see if you guys can do one more practice without me so much. Take a minute and find the other two functions. Just real briefly, 4t cubed minus 6t plus 2. That good? I don't really want to write all of that stuff out anymore. You just bring the exponent down to the front, subtract 1 from it, write it out. Bring the exponent down, 2 times 3 is 6, subtract 1 from it, get t. Similarly, 3 times 4 is 12. T, 3 minus 1 is 2, minus 6. Those are our two functions. Not terrible, I hope. Some little things to keep in mind. This number has to be in meters per seconds cubed. Actually, meters per second to the 4th. So that when you multiply all that out, you get meters per second. In the same way that this number has to be in meters per second squared, so that when I multiply it out, I get something left in meters. The units still have to be here. They're just weirder units. Also, you kind of need to have some expectations about what the shapes of these functions are. Like a t to the 4th function can have something like that. And a t to the 3rd function can have something like that. You're supposed to be aware of moderately these shapes, because there's other things that could be asked of us. Like between time equals 0 and time equals 4, what's the fastest it's going? Or is there a local maximum or a local minimum? Have you heard of these things before? Because these are things that could come up. We're not going to spend much time on that at all. But in a future class, those are the kinds of things that could be brought up and discussed. Does that make sense? In here, we can take our function downwards by taking the derivative and move upwards by doing the antiderivative. But I want to see if you can do one more thing. can you do this? If I give you that one, can you go in either direction? Try. Okay, so I'm gonna assume that this was not terrible, but I hate assuming that, so I should wander around. This one should have been easy, because we've been doing this one. Let's try going the other direction. One thing to keep in mind is that when you go the other direction, when you're finding the antiderivative of a polynomial, when you're done, you should be able to take the derivative and go back and see the same thing. So the process has to go backwards. So we add 1 to the exponent, but then we have to divide by that new exponent. Now that's the process for going backwards. For example, t to the third power. I've added 1 to the exponent. But now I have to divide 12 by 3 and get 4. And check with the derivative to make sure you get back 12t squared when you go back the other way. And you clearly will. You'll bring the 3 down. 3 times 4 will be 12. Subtract 1 from 3 and you get 2. It works. I think we'll be okay here, 4t squared. Remember, the 7 is t to the 0 power. So because it's t to the 0 power, I add 1 to the t, and then, 1 to the exponent, and then divide 7 by 1. I'd love to say we're done, but we're not. We don't know if there was a constant there or not. When the derivative was taken to create the velocity function, there could have been a constant. We don't know where the object actually began its motion, so we add the boundary condition. Add the constant, knowing it's got to be the initial position of the object. Have something there to represent that. Now, going this way is taking the derivative. Truthfully, going this way is taking the integral. I'm skipping I'm taking some liberties. So for just a moment, let me just grab this function and show you what I'm supposed to do here. I'm supposed to replace a with its differential. That's what I'm supposed to do. Then, and this is important, I'm supposed to split the derivative. Then, I'm supposed to use symbology that instructs you about taking the integral. integral symbol, which is actually taking a sum. Now the left side is taking the integral of dv. This is v to the 0 power. Right, there's nothing there, so there's an implied 1. An implied 1 suggests something to the 0 power. Since we're talking about v, it's v to the 0 power. In the same way that there's an implied t to the 0 power here. The first step in taking an integral is to find the antiderivative. So on the left side, increase the exponent by 1 and divide by the new exponent. It's just v. The right side is one that is going to be more valuable. We knew we were going to get v. We're going to get the velocity function. Add 1 to the exponent, divide by the new exponent. Add 1 to the new exponent, divide by the new exponent. And make sure you recognize, that there is a constant that might have disappeared during the process. And it represents the initial velocity. That's what you're supposed to do. That's the whole, the whole symbology of the process. In practice, this symbology is largely ornamental for what we're doing. Finding the antiderivative function and the derivative function can be done right on the same line, just like we're doing or have. I know some of you are going to have calculus or are having it now. I like to make sure that I'm telling you that you're going to learn a more formal way to represent this and to communicate integrals to a person who's going to be grading your papers. Later this year, we will be doing integration like this. And so I want you to be prepared to know that this is the actual formal process. But for your homework, my plan is to give you something that is relatively simple, like velocity equals 6t squared plus 4t minus 1. And tell you that this object is at the origin at t equals 0, and ask you to come up with the position function and the acceleration function. I suspect you can do that right now, that you have all the capabilities of creating those two functions, probably without having to do a lot of fancy symbology. It's our last practice for today.
Is that a 6?
6t squared plus 4t minus 1. Also be aware, I've been very kind with the numbers. You recognize that. There's no reason for that. I've made sure everything divides out into nice little integers and stuff, but there's no reason to accept that that'll have to be the case. Any questions about my answers? They look good. Notice why I didn't put an x naught there. I don't have to. I was given the boundary condition. I was told the object's at the origin at time equals 0. The origin is 0, so I did not put a plus 0 here or plus x naught, not if I'm given an initial condition. If I'm given the initial condition, use it. All right. I have homework that corresponds with this, and I'm going to be posting it. It has more in it than just this, but it's mostly just this. I think it's 5 or 6 different examples of this over and over again with further questions like where is the object when the velocity is 0? I want you to recognize that you may have to be able to find the zeros of a complicated function. You understand that, right? You may have cubed functions, a function to the fourth, stuff like that. Don't sweat that stuff. That's not going to be on any test. This is going to be on the test, finding these functions. That's what's on the test. Use your calculator, Desmos, something to find the zeros if you have to. Don't make that the hard part of the homework. Good job today.